Hey there, STEM Chemistry. This is Miss Ruark. This is Vodcast 6.3, where we're going to talk about limiting reactants and percent yield. So we're still doing stoichiometry. We're just taking it another step further. Okay, caution. This is some bad stuff, right? Okay, now, I like the hand sticking out of the alligator's mouth. Okay, this stuff is difficult to follow at first, so please be patient. Some of you are going to get it immediately. Some of you are going to be like, well, Miss Ruark, what are you teaching us? Bear with me, okay? Bear with me. Don't give up. All right, so when you're doing a recipe, when you're cooking something, let's say we're making a cake, we need 2 cups of flour, 2 eggs, a cup of sugar, 1.5 tablespoons of baking powder, a cup of water, and a third a cup of oil. Let's say that in your kitchen you only have 14 cups of flour, you have 14 of these, you have 4 eggs, you have 9 cups of sugar, you have 15 tablespoons of baking powder, you have 10 cups of water, and you have 3 1/3 cups of oil. And the question is, well, how many cakes can you make from that? Well, let's see. If it was based on just the flour recipe, we can make 7 cakes, but based on the eggs, we can only make 2 cakes. So we need to figure out which one is our limiting reactant, which one is going to limit us. So suppose with the flour you need 2 cups, you have 14 cups. You can make a total of 7 cakes. With the eggs, if you need 2 eggs but you have 4, you can make 2 cakes. With the sugar, if you need 1 cup, you have 9, you can make 9 cakes. With the baking powder, you need 1.5 tablespoons. If you have 15 tablespoons, you can make a total of 10 cakes. Water, you can make 10 cakes. And for a third, you can make a total of 11 cakes. So which one's going to run out first? Well, guess what? Our eggs runs out first. This is the one that's going to limit us from making more. So it is our limiting reactant. And based on just the number of eggs we have, we can only make 2 cakes. All right, so how many can we make? Answer is 2 cakes. Why? Because the eggs run out first. They are our limiting reactant. Okay, only 4 eggs, blah, 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 blah. Okay, oh, I forgot I had all this extra stuff here. Sorry. Okay, moving on. So how do we use this with chemistry? Well, with chemistry, question number 1 says, how many moles of nitrogen monoxide are produced? So we know we're going to make nitrogen monoxide on this side. If blank moles of NH3 are burned in blank moles of oxygen. So we've got ammonium burning in the presence of oxygen, and it's going to produce nitrogen monoxide. And does anybody recognize what kind of a reaction this is? Probably not, right? That's okay if you didn't. We're going to make water and nitrogen monoxide, so this is a combustion reaction. A combustion reaction. It's a nitrogen hydride rather than a hydrocarbon. So that's okay. All right, to balance this out, you can pause it and go on ahead and balance it and come back and check your work if you want. It is going to take a couple extra steps, and I don't want to waste the time on it. I want to make sure we do the stoichiometry. So for that case, I'm going to go on ahead and write in our coefficients. 4, 5, a 6 for the hydrogen, or for the water, and a 4 for the nitrogen monoxide. Okay. So the question is, how many moles of nitrogen monoxide are we going to produce if we have 4 moles of ammonia and we have 5 moles of water reacting? Okay, so we have to go from moles to moles. So let's see which one we get. So we've got 4 moles. Where'd my pen go? It left. There it is. Okay. We have 4 moles of ammonia, and we need to go from moles of ammonia to moles of nitrogen monoxide. So moles of ammonia goes on bottom. Nothing new here, right? Moles of nitrogen monoxide goes on top because that's what we're looking for. All right. And then what numbers do we put here? That's our mole ratio. So we come up here, we put a 4, and we put a 4. Yay, 4 and a 4. Oh, look, that makes it so easy. We can make 4 moles of nitrogen monoxide. All right, well, what about if we had 5 moles of oxygen? Okay, so we put moles of oxygen on bottom, and we put moles of nitrogen monoxide on top. 6 for nitrogen monoxide, and not 6, sorry, 4 for nitrogen monoxide, and 5 for oxygen. And so 5 divided by 5 times 1 is 4. How neat is that? All right, so in this case, look, we're going to use up both of our reactants to completion, and we're going to end up making 4 moles of nitrogen monoxide. How sweet is that? Now guess what, guys? It doesn't always work that way. It's not a perfect world. You guys know that. Okay, so let's see what happens if we have 4 moles of ammonia, and we've already figured that out. We said we can make 4 moles of nitrogen monoxide. Right? We did that earlier, so I'm not going to do it again. Well, what if we have 20 moles of oxygen this time? Okay, so 20 moles of oxygen, we put moles of oxygen on bottom, and we put moles of nitrogen monoxide on top. We put 4 and 5, and this will end up giving us 80 divided by 5, and that gives us 16. Sorry, I had to think about that one for a second. All right, so this one gives us 16, this one gives us 4. And based on this is how much we're going to make. We can't make more because we don't have enough parts, right? So this is our limiting reactant. Now let's try another one. Here we have 8 moles. With 8 moles of ammonia, guess what? We're going to double that number and make 8 moles of nitrogen monoxide. 20 moles of oxygen, we said it would make 16 moles of nitrogen monoxide, right? So how many can we actually make? Well, we can only make 8 moles of nitrogen monoxide because the ammonia limits us from making more. All right, you have an example 2 in your notes. You can pause and try that one. I'm going to move on. All right, so example 3, how many grams, so we're looking for grams of nitrogen monoxide, are produced if 4 moles of NH3 burn with 20 moles of O2? All right, so we know that NH3 is our limiting reagent. Okay, reagent, reactant, same thing. We know that that's our limiting reactant. So, and we know that because of this side, we did it here. Okay, so we know that since that's our limiting reactant, that's the one that's going to run out first. So we're going to use it to determine our final answer. And since NH3 is our reactant, our limiting reactant, we use it. This one is what we say is in excess. We don't need to worry about it. Okay, so we use 4 moles of NH3. And we go from moles of NH3 to moles of NO. Nothing new here, right? We're good. 4 and a 4 ratio, right? You have it written down on your paper. Okay, and then we go from moles of NO to grams of NO because we're looking for grams, right? And 14.01 plus 16 gives us 30.01. Moles cancel, we're left with grams of NO. All right, so then we do the math. 4 times 4 is 16 divided by 4 is 4 times, so 4 times 30, and so it should be like 120.04, I think, right? One significant figure, we're going to make approximately 100 grams of nitrogen monoxide. Okay, now remember, if I'm going too fast through this, please pause it. Don't hesitate to pause it, rewatch it, rewind if you need to. Okay, so what happens if we end up with 2 things that we aren't sure which one's going to run out first? Okay, so I'm going to show you one way to do this, which is what we would say the long way, and then there's a shortcut way I'm going to show you on the next one. All right, so on this one, step 1, you need to calculate the number of moles for each reactant. Well, we have 30 grams of O2 and we have 20 grams of NH3, and we want to know how many grams of NO are we making. So we're going to go from 20 grams of NH3, and we need to go to moles. So we're going to put the formula mass or molar mass on bottom, 17.04 grams of NH3, 1 mole of NH3 on top, and we're going to solve for it. Okay? And when you plug that into the calculator, you end up with 1.17 moles of NH3. So that's how much we have. This is how much we have. All right, well, what about our oxygen? We have 30 grams of oxygen. We're going to change that to moles of oxygen, and since it's O2, it's going to be 2 oxygens, so 32.0 grams of O2. Okay, when we plug that into the calculator, we get 0.9375 moles of O2. And remember, this is how much we have. Okay, this is how much we have. Well, looking at our balance, well, let's keep going. Next page says, we have 1.17 moles of NH3, we have 0.9375 9.375 moles of oxygen, and we're going to compare these. Looking at our balanced chemical equation, remember this is what we have. We need 4 moles of NH3 to react completely with 5 moles of O2. Okay, so just by comparing, do we have enough if we did a 4-to-5 ratio? And look, this right here is not enough. We would need more oxygen than ammonia, because we need more oxygen than ammonia to react. And since this isn't enough, this would be considered our limiting reactant. And we figure that out by comparison. Okay, so now we're going to perform the stoichiometry by using our limiting reactant as the given quantity that we would use to solve the problem. Okay, so, and we don't have to start at the grams. We've already got moles, so we can just use the moles, 9.375 moles of O2. And we're going to go from moles of O2 until we get to, grams of NO. So now we do our mole ratio. There's 5 moles of O2 to 4 moles of NO, and we need to go from moles to grams. So 1 mole of NO is equal to 30.01 grams of NO. Right. And then now we just need to solve for it. And the calculator gives us 22.5075. But we started with one significant figure, so we need to make sure this has one significant figure in it. So we're going to make approximately 20 grams of nitrogen monoxide. And we have to base it on the oxygen because the oxygen is what runs out first. Okay, how can we do it the shortcut way? Well, the shortcut way is if you take it and you do 2 separate calculations, or 3, however many numbers you have as your reactants, and the one with the smallest answer is the correct answer. Okay, so when you set this, I'm not going to do this one for you, but you can do it. Do 20 grams of ammonia and go all the way until you get to grams of NO. And then do 30 grams of oxygen and go all the way until you get to grams of NO. And the one that's smallest, which should be this one right here, is your limiting reactant. And that's how you determine your limiting reactant and your final answer. Okay, now the reason I'm not going to show you that is because I need to move on. But we can check our work and you can show me what you did when you get to class. Okay, here's another one for the shortcut. Go ahead and do this one on your own and we will check your work when you get to class. Okay, yield. So what is yield? Well, yield is the amount of product that's made in a chemical reaction. Remember, the arrow stands for yield. So there's 3 types of yield. There's an actual yield, which is what you actually get, you measure, you make in the lab. Theoretical yield is what the balanced chemical equation tells you should be made in a perfect world with perfect conditions. And then we have percent yield. And percent yield is just the percent of the product that's made. And it tells you, well, that gets into it on the next page. Okay, so it tells you the percentage of product that's made based on what you should make. Okay, percent yield tells us how good a reaction is, because some reactions are good and some are really bad. Percent yield cannot be bigger than 100% unless contamination occurs. Okay, so the only way that you get something that's greater than 100% is if your sample that you made is contaminated in one way, shape, or form, meaning it has more stuff in it than it needs to. Theoretical yield will always be larger than actual yield, and the question is why? Well, you can have impure reactants, you can have competing side reactions that happen that kind of take away from your product, loss of product through filtering or transferring between containers, and these are just some of the reasons why. Okay, so here's an example. It says, oops, no, go back. Okay, we have this much right here. We have copper that is being produced, and it says that aluminum is reacting with excess copper to sulfate. Okay, so it looks like a single replacement reaction to me, which means we're going to make aluminum sulfate as a product. And then you need to balance it. All right, so I want you to go ahead and solve this as a stoichiometry problem to figure out what your theoretical yield should be. You're going to pause it. I'm going to pause it. We're going to come back and check your work. All right, so this is what you should have gotten. This is our theoretical yield, which is 13.85 grams of copper. That's what you should make. What we did make in the lab was 6.78 grams of copper. And then we have to figure out our percent yield. So actual over theoretical times 100. All right, so actual over theoretical, we make about 49% copper. That's not really a good yield, so it's not really a good reaction, and we need to find a new one. All right, I'll see you in class.